Hello everyone, today I'm going to talk about my final project. The topic is handwritten digits recognition with multilayer perceptron. Um, in this project, I tried to figure out the most suitable model for my dataset, which is processed from monastic database. The exacting experiments work includes initialization of network, comparing batch learning and online learning, normalization of input, early stopping criteria implementation, adjustment of learning rate parameter, and comparing of different hidden neurons and hidden layers. Finally, finally, in this project, I get 100% prediction accuracy on the training set and more than 95% prediction accuracy on testing set, which is a pretty good performance. In practical, handwritten digit recognition have many useful applications in postal mail sorting and bank check processing, etc. So, at the beginning of my project, I do the initialization of the model. The first part is to pre-process the data. The dataset I use for training and testing my multilayer perceptron is derived from the MNST database of handwritten digits. All digits pictures have been size normalized and centered in a fixed size image of 28 by 28 pixels. The pixels values are from 0 to 255, in which 0 means black and 255 means white. Then I resize the 28 by 28 pixels into 20 by 20 pixels, so I can reduce the input features from 784 to 400. And I randomly choose 20,000 examples from the 60,000 examples to speed up my training process. As we can see from the picture, even though we use less pixels to illustrate the digits, the new one also contains enough information to recognize the number, which gives me confidence on my pre-processing. And of course, reduce the feature dimension can help me to speed up my training task. Then I initialized the multilayer perceptron. Um, I choose the input layer to have 400 units because we use the 20 times 20 pictures, and I choose the hidden layer to have 155 units, the output layer to have 10 units because we have 10 digit number, 0 to 1. And then I do the initialization of weights. It is easily to find that we cannot use O1 or O0 to be initial weights, which would break down our backpropagation algorithm. So a good solution is to pick synaptic weights from a uniform distribution, which has 0 as its meaning value, and have the standard deviation of the induced local field size as variations. So I choose the equations below to initialize the weight, and the function I use in MATLAB is also shown here. And next, I choose the activation function. An example of continuously differentiable nonlinear activation function commonly used in multilayer perceptron is sigmoid function. What I would like to use in this phase is a typical format of that. Is the logistic function. It's defined like in the following, and the right picture we can see is the plot of that logistic function, and it's easy to find that the output value in the network have nonlinear distribution in the interval 0 to 1, and I would like to talk about that behind. Then is the forward computation. We can see the left picture below, this output is computed with the initial weights, and we will use the backpropagation algorithm to reduce the error energy by iterations. As indicated in the previous part, the output value is from the interval 0 to 1. And the left and the right picture is just how we can present our desired output in the mathematical form. And the above picture is what I used in MATLAB. Then I do the gradient descent. As indicated before, we use backpropagation algorithm to compute the gradient descent. So we also need the learning rate parameter eta to decide the correction of weights, which is so-called the delta rule. The delta rule is the equation above. And as we can see, A1 is just the input of our network, and Z2 is the output of the input layer, and A2 is the input of the hidden layer, etc. So finally we got A3 to be our output, to be our final output in the network. And we use the following equation to solve the gradient, and we finally got this gradient. And then I like to talk about the batch learning and the online learning. I want to compare those two learning methods and to choose a better one for our project. First, I like to talk about the batch learning. We assume that there are n examples in our training set. The batch learning adjusts synaptic weights of the multilayer perceptron after all the n examples are presented in one epoch training. And from the left picture and the table 1, we can see it is obvious that learning rate of 0.2 and 0.3 are more suitable for this batch learning. The higher rate, like 0.4 and 0.5, would make weight space unstable. And then let's see the right picture about the online learning. In the online learning, we adjust weights of multilayer perceptron after each example. So the cost function is the total instantaneous error energy, E of n, that need to be minimized. So let's consider n training examples in an epoch. When the first example comes into the network, we adjust the weight using gradient descent, and then we do this step in further examples, iterations by iterations, and we finally got the final result. From the picture, we can see that the rate 0.01 and 0.05 is too large for this online learning, so that the cost cannot be conducted with gradient descent. Also, the rate 0.001 is a little unstable. So the 0.00001 and 0.001 can make a smooth descent in every surface, but the first one is a little bit slow. So we choose the 0.001 to be our learning rate. And from the table 2, we can see that with 96.44 accuracy on training set and 93.82% accuracy on testing set, the learning rates 0.001 under online learning satisfy our network with a good result. So I would like to choose the online learning and 0.001 to be my learning rate in this architecture. Then I do the inputs normalization in order to improve the performance of my model. And the first step of input normalization is to remove the mean value. Uh, so for each feature in every example, I use its value to minus their mean value to be my desired to be my desired result in this step. And the second step is the feature scale. The simple method is to scale each input into similar range. So I use the result in the step 1 to divide 255. And after normalization, the learning process gets much higher learning rate, and the rate 0.01 does really a good job with fast decreasing and maintain smooth and stable change in weight space. 0.05 also performs well, but it is a little unstable. And in the table, it is easy to find that the learning rates 0.1 and 0.5 is both show good results on prediction accuracy. However, we could see that the curve slows and flattens after 14 epoch at rate 0.1, while it's flattened after 20 epoch at rate 0.5. So the rate 0.1 gives us a faster decreasing. Now, after normalizing the inputs, rate 0.1 show me a faster and stable learning curve with a good performance on prediction, which is 100% accuracy in the training set and 97.54 accuracy in testing set. And then I do the stopping criteria with cross-validation because sometimes our model will be overtraining. Sometimes the network seems to perform better. For example, the error signal decreases, but at some point during the training, it's actually start getting worse again. So a simple way to avoid overfitting is called early stopping method of training. And in this project, I choose GL method, which is defined in the first equation. In this equation, EVA of t means the per example error at present iteration, and the EOPT of t means the minimum error value so far. So one of the obvious reasons to stop training is the high generalization loss, because it is clearly means overtraining. Accordingly, we get the stopping criteria. If the generalization loss reaches a certain threshold, we stop training as soon as possible. And here we define the threshold as GL alpha, and the stop iterations and we stop iterations after GL is greater than GL alpha. I choose GL alpha is equal to 7 in this project. And then I use the weights in previous if the rate flattened, I use the weights in previous iterations. And here to do the prediction on training set and testing set, I got 100% and 97.50% separately for the training set and testing set. The next step, what I do is to adjust the learning rate to see which learning rate is to find a better way to define the learning rate. The first method is use the momentum term. This method simply is to increase the learning rate while keep the curve stable. The definition is the equation above, and it's also called the generalized delta rule and alpha is the momentum term, where 0 is where alpha is between 0 and 1. In this picture, the wider black line is the original learning curve without momentum term. When alpha is positive, all curves are above all curves are above the original curve, and things get even worse. So when alpha is negative, the curves are relatively smoother and get fast decreasing rate. The curve gets to be slow and flattened after 10 epochs when alpha equals to minus 0.5. So it is an improvement compared to rate 0.1, which is flattened after 14 epochs. The second method to adjust the learning rate is called search then converge schedule. It's also called STC. The definition is in the left equation. And the basic idea of that is because the gradient descent with a constant rate is not a good enough strategy, so we could use the large rate at the beginning epochs, but with iterations increasing, we need to reduce the learn rate in order to make sure the stable change in weight space. So um, the method is to refine this to use a time varying learning rate. And from the picture, we can see that it's obvious that when tau is equal to 10, it gives us the best result with fast decreasing and smooth curve, which flattened after 9 epochs. The curve flattened after 9 epochs and stopped at 14th epoch. So now our prediction accuracy is 100% on the training set and 97.56% on the testing set. Then I tried different hidden units number and different hidden layer numbers, and I tried to figure out which is the optimal set in the network. And then I find out the initial model is the best among all my tests, which is 400 units to be in the input layer, 150 units in the hidden layer, and 10 units in the output layer. So this is the final result I get from combining all the parameters we talked about. And this is the main function I use. First, initialize the weights between the hidden layer and input layer and output layers to hidden layer, and I use the cost function to do the to compute the cost between our prediction result and the desired result. And this FMINCG is the optimization function. Then I predict the results and calculate the accuracy. So eventually, I chose 3 layer models with 400 input units, 150 hidden units, and 10 output units to be my final model. And I implemented this model on the whole MNIST database. There are 60,000 examples in this training set and 10,000 examples in this testing set. In order to use the GL early stopping method, I split training set into 50,000 examples training set and 10,000 example cross validation set. With input normalization, learning rate eta equal to 0.5, momentum term alpha equals to minus 0.5, STC schedule parameter tau equals to 10, GL early stopping parameter GL alpha equals to 7. I got learning curve under online learning like the following, which stopped at 16th epoch. So this graph is the final learning curve training by the N9ST database. Thanks for watching.